Welcome to the first of what I hope will be a series of recordings on how to become a rocket scientist. Now, I recognize that some of you may feel like that's not something you want to do, and if so, that's fine. But I want you to consider the fact that it may not be as hard as you think. You see these t-shirts all the time that I am a rocket scientist, or you'd have to be a rocket scientist to understand this. And it turns out that most of the things you need to know to be a rocket scientist aren't that hard and really don't go much beyond first level calculus, if they go much into that at all. Oh, but they kind of do. So I recognize that you may not be into a lot of math, so I'm going to try to make this first episode, which is going to be about escape velocity, how to calculate escape velocity, to be as simple as I can make it. There will be some math, but most of that math, except for the integration part, you should really be very familiar with. And even the integration part, if you can just accept the answer of that operation, it probably will still look familiar to you. And I think it'll be kind of, fun in not a theme park sort of way, but I think you'll find it interesting. So without further ado, and sponsored by dspwidgets.com, we're going to take you from the DSP labs here to an explanation of how to be a rocket scientist and how to compute escape velocity. Thank you. Okay, let's get started. So first of all, let's talk about what we mean when we say escape velocity. So really what happens if, let's say we have the planet Earth, and somewhere on Earth there's this little tiny guy here, and that person throws a ball upward into the sky. Now, we would expect that ball to attain a certain height and come back, and it's pretty intuitive that the faster that they get the ball to leave their hand, the higher it'll go. But alas, all things that go up must come down, or so the conventional wisdom is, and so that ball is going to return to Earth. However, consider the case where the ball is sent so fast that it reaches such an altitude where it escapes the planet. So what do I mean by escape? Well, assuming that we neglect the influence of all of the other planets in the solar system, what we mean by this Okay, so let's get started. So what do I mean by escape velocity? Well, assume that you're on the planet Earth, which may be quite an assumption for some of us, and here you are and you throw a ball up into the air. Now, obviously, if you throw the ball hard, it may go up very high, and it makes intuitive sense that if you throw it faster and harder, it'll go up even higher. But it doesn't make much sense for ordinary experience that the ball would never return. But in fact, it does make sense that there seems to be an altitude somewhere out there above the Earth in which we know about zero gravity, so-called zero gravity. In other words, and in fact, it's not really zero gravity, but the gravity influence is so low that the object falls incredibly slowly, and therefore it seems like it almost won't come back to Earth. Well, it turns out that if you could throw the ball fast enough, you could get it so that, not respecting any other influences like the pull of other planets changing its trajectory, this object would go on out into space forever and never return back to the planet Earth. So how would we go about calculating? What we want to calculate is the velocity v, and I'm going to put little e, escape, the escape velocity, and that would be the velocity that we need the object to initially have upon it leaving our hand to go out into space, escape the Earth, and to travel out there forever. Okay, well, I'm going to first of all introduce the whole concept of quantitating gravity. And gravity is a force that we intuitively know that acts upon an object. It turns out that force can be computed from other things, and one of them is the gravitational constant, and then the mass of the first object times the mass of the second object. So we have gravity times the mass of one object times the mass of the other, divided by r squared. And that's the distance in between the two objects. So we've introduced this concept of amongst two objects there exists a force. And it turns out that force pulls on each of the objects to pull them together. And that force is based on their mass. Well, what's mass? Well, it's simply a property of matter, a property of atoms, property of the constituent parts of atoms, that they all have some mass. And we intuitively think of that mass as weight. But it's not quite the same thing, because weight is in fact a force. Weight is in fact the result of the object's mass being pulled into the object Earth. And that is why the weight of an object on Earth may be considerably less, say, on the moon, because the moon has less mass than the Earth, and therefore the attraction between the two of them is less. So we see a difference between mass, which is a property of matter, and the force, or weight, which is the value of the forces between the objects. So now that we have this handy formula, it doesn't look too bad. We say, well, okay, we learned a long time ago that in basic physics that energy, or the amount of work we have to do on an object, is equal to the force that the object resists when we try to apply pressure to the object, times the distance over which we move the object. This is one simple definition. So if you move an object weighing 1 kilogram and if you move an object and it takes you 1 Newton of force, that's the appropriate number I'm looking for, and you move it 1 meter, you've done 1 joule of work, or of energy on that object. So energy is equal to force times distance. So having that definition, we're going to use energy as sort of an intermediate way to compute this escape velocity. How? Because we know one other thing about how we can compute energy. The energy of a moving object is equal to 1/2 times the mass of the object times the velocity squared. Now, this can be derived very simply from the old F equals ma equation, basic Newton equation, and a little calculus. You can get to this, but we're not going to do that here. So this is a given formula, and this is a given formula, and this is a given formula. So now we have these formulas that we can put to work for us. And so I'm going to suggest that the energy then, the total energy of moving this object all the way out into space until it has escaped the Earth, is equal to the sum from the start to the finish of moving, each time the ball moves a little bit, some delta distance, but delta d, times the force that acted on the object. Now imagine that we do this again and again, repeat this calculation. Every time the ball moves up an inch into space, we calculate the force that was on it. Now the reason we do it that way is the force isn't constant, because the force varies the farther the object gets away from us. So we have a varying force over time. And so we have to kind of recompute the force every time we compute this formula for a small distance, and then do it again and again. Well, if you've had any integral calculus at all, you recognize that this is an integral equation. And so we're going to express it a different way, a little more reasonable way. We're going to say that it's equal to the integral of this delta distance, which we're going to call dr. That's what that little d something means in integral calculus. It's a small movement of the variable of integration. And we're going to multiply that times the force, which we know to be an equation. And we're going to put the limits of this integral as, well, so what is r? Well, r is the distance from something. So if your mass is still at the Earth, is the distance 0? Well, it turns out not really, because the Earth is big, and because you can approximate all of the mass of the Earth as though it were at a really infinitesimal center point of the Earth. Why? Well, if you want to convince yourself that's true, break the Earth up into a million little spheres, all compacted together, and then do the calculations for each one of these evenly distributed about the center. And you'll find that if you make that laborious calculation, you'll find it's the same as one calculation using all of the mass concentrated at the center. So we can talk about principles of symmetry, and or we can do the math, but for now just accept that for large masses, and especially for distances between the masses as being larger than the mass itself, the diameter of the mass itself, this is not an important parameter. But at the starting point, this one is kind of important. And so the actual distance here from the center is the radius of the Earth itself. So we're going to say we're going to start at the radius of the Earth. And if our object never returns, then the distance it goes from the Earth is infinity. Okay, so now we can replace this F equation. We can replace the F with the equation, and we get the energy total is equal to, but before I put F, before I put F here, replace it with the F up here, I'm going to do a little magic. This gravitational constant is just that, it's a constant. And in our case, the mass of the Earth and the mass of the object don't change as time progresses or as the radius increases. So these are all constants in the integration. So they can be moved outside integration. It's just a math trick, but they don't have a direct effect during the integration. So we say the gravitational constant times mass 1. So we're going to go ahead and say mass of the Earth times mass 2, we'll call that the mass of the ball, okay, times the integration and starting at the radius of the Earth to infinity, and then what's left of this equation is just 1 over r squared dr. There we go. So fundamentally, this equation is what we're left with to calculate the total energy. Okay, coming back, and now I've used I just simply recopied the equation to a fresh page. And so now we actually get to do the math. And this is where things may get a little hard for some of you who've forgotten basic college calculus, but this is just an integral. It's really easy to do, but basically you look at this element right here and you see that 1 over r squared is the same as r to the minus 2. And we know that if we want to integrate that, we add 1 to this. So now this is going to become minus 1. And we divide out by the new power, which is minus 1. So this is the integration. This is non-specific integration of this value. And if we want the actual values, we have to say we want to integrate starting from the radius of the Earth out to infinity. Now, all of this is times this g mass of the Earth, mass of the ball. Now, what we're going to do with this is we're going to plug this number in, and then we're going to subtract from it. This is like how you take the limits of integration and get a specific number. So you plug this value in, into this and compute it, and then you plug this value in and you subtract it from the previous value. Well, when r is infinity, 1 over infinity is 0. And so this first term just goes away, yields 0. And when r is equal to re, the radius of the Earth, then we have to subtract this value out because it's the bottom level of the integration. So we get minus 1 over re. The thing is, there's a minus sign in front of here, so that's what happens. So we see this comes out to a pretty simple thing, and this is what was in here. So if we multiply it times G, ME, MB, what we get is that the energy total is equal to gravitational constant, mass of the Earth, mass of the ball, divided by the radius of the Earth. Pretty simple. So this is a nice equation, but it didn't give us velocity. But remember that we said that the energy stored in an object is equal to 1/2 times the mass times the velocity of that object squared. Turns out that's a calculus result of F equals ma. Can easily be derived. So we use this. We say this energy has got to equal this energy because we're throwing the ball up in the air, we're giving it an initial velocity, but there's nothing else to act on it later once it leaves our hands. So it better have all the energy it needs when it leaves our hands. So we say that, well, 1/2 mv squared must equal g me mb. Oops. Didn't make that a subscript, did I? mb over re. And this mass is the mass of the ball because it's the one that has the velocity as it's being thrown. So immediately we see this cancels, and we can get rid of this 1/2, put a 2 out in front, and we see that v squared is equal to 2g mass of the Earth over re, or v is equal to 2g mass of the Earth over re square root of. All right, that's all there is to that. Okay, so offline I've taken the opportunity to write the mass of the Earth, to go look it up and write it down. We're using the meters, kilograms, second MKS system of physics. So I've written this as kilograms. It's 5.983 times 10 to the 24th kilograms. The radius of the Earth is 6.371 times 10 to the 6 meters, if it were more or less approximated to a sphere. And the gravitational constant is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. So, by the way, one other number you kind of need, it's kind of nice to have, is that 1 mile is equal to 0.6309 kilometers. So, if we plug these numbers into this equation, what we get is we get that the velocity is equal to 11.192 kilogram or kilometers per second. Okay, so to get to miles per hour, you would multiply this times this, and you would multiply the whole thing by 3,600 because there's 3,600 seconds in an hour. And what that gives you is 25, I have to use my little HP calculator here, 25,421 miles per hour is equal to the velocity. So what does this mean? It means that if you could throw a ball such that when it left your hand, it had 25,421 miles per hour speed, it would go out, and you threw it straight up, it would go out into space and never return, neglecting that it came close to other spheres of influence. In this case, spheres literally means planets or other objects in space that might bend or curve its trajectory. So that's a pretty interesting result, and it turns out that's pretty useful for scientists, engineers, and rocket scientists to figure out just how hard is it to get off a planet. And you can see, because of the r² term on the previous slides for force, that a lot of the energy is expended very close to the Earth, which is why a lot of the strategies for getting farther out into space is to build a space station near Earth and then get up to that level, and then have the space station be a staging area to assemble a much larger rocket and then go from there. So we saw also that the mass of the object fell out. Does that mean that it doesn't matter? That means we can make the object as heavy as we can? Well, yes, for escape velocity, for the velocity, that's what it says, but it's not true of force. So the problem here is that the mass canceled out in the energy equation, but it doesn't cancel out in the force equation. So the heavier the object is that you want to send out into space, the more force you need, which means the more fuel you have to put on board, which means the heavier still the object becomes, which means you still need more force to lift the fuel that's not yet burned. The good news is, as you expend that fuel, the object gets lighter and lighter, but it also gets further and further away. So that's why I say when you see the picture of the Apollo 11 shots, when it first fires up and lifts off the pad, it doesn't seem to be going very fast at all. It's just barely enough to move. It has enough force to start in motion, but it is not going very slow. But fortunately, by the time it clears the tower, it's going a lot faster. But it's also used up a significant portion of the fuel just to get several stories high. So weight is everything when it comes to launching a rocket. But in this case, we really made an equation for more something like muzzle velocity, where we're only interested in the initial energy that it takes. And so that's the calculation, and now you know how to do it more or less. And so you've taken the first important step into becoming a rocket scientist. I hope you found this interesting. Perhaps not like a party, but I hope you feel like you know something now that you didn't know before. Anyway, look for more on my series. Thank you for listening.